So, today we're starting chapter 10. So, chapter 10 is about parametric and polar functions. So, today we're going to be talking about parametric functions. So, let's try to stop talking, please, and focus in here now. I know, it's the end of the day, it's been a long week, everybody's pooped. Got to do it, though. Okay? So let's start by defining what we mean by a parametric function. Okay, so we say that the graph of the ordered pairs xy, where x is defined by the function f of t, and y is defined by the function g of t, are functions defined on an interval of values for t. That is called a parametric curve. So those two functions, f of t and g of t, are called parametric equations. And t is called the parameter, and I is called the parameter interval. Okay, I'll give everybody a chance to it's a lot of writing there all at once. We'll give you guys a chance to kind of write some stuff down, and then I'll kind of talk a little bit more and write out specifically a specific parametric function. And then we'll talk about how we can graph some of these things on our calculator so you get an idea of what they look like and why you should care about this. Or, well, maybe why mathematicians should care about this. Maybe you in particular won't care, but the greater mathematics community cares about this. You know what I mean? It's not exactly what happened on The Bachelor last night, but I know that happened on Monday. I know. It's Thursday.
Do you watch it?
Yeah.
Really?
Me and my wife.
Who do you want to win?
I hate them all.
Even Madison?
Yes.
You don't like her?
No.
You don't like Madison?
No.
The Bachelor.
Okay, but if
Do you like Peter so much?
No.
I don't like Peter.
Kelly was the best girl this
Yeah,
season.
but then she got too cocky. She got too arrogant.
Yeah, I agree. Yeah.
I don't think it's cocky if it's true.
Oh.
All right. So, for example, we have like the Cartesian equation, y equals x squared, right? This is like what you would have done in, your algebra class. We can rewrite this as a parametric function where we're going to have two equations, one that tells us how to find our x coordinate and one of them that tells us how to find our y coordinate. And then we have to list what values of t we're going to plug in. So typically we describe those values of t as using an interval notation. Okay? So this is our parametric version over here. Okay? So anything you can graph using the Cartesian form, we can also graph using the parametric form. The advantage of the parametric form is there's many things that are very difficult to graph in a Cartesian form that we can graph quite easily in a parametric form. So that's the advantage here, is it's more general, it gives us more flexibility. So let's show you guys an example of that using our calculator, because our calculator can graph these kinds of parametric equations quite easily. So let's say that we have the parametric equation, x is equal to t squared plus 1, and y is equal to 2t. And we're going to graph this over 3 different intervals of t. So we're going to do this all on our calculator. So if you have your graphing calculator with you, I invite you to take that out and you can follow along. If you prefer to just sit and listen, perfectly fine to do that as well. Although my suggestion when it comes time to look at the homework, you may want to cue this video back up and watch the buttons and whatever. Okay? So the first thing we're going to do is we're going to press the mode button on our calculator. Now notice the options there right in the middle of our calculator. There's 4 options. One of them says func, par, pol, and seek. Func is short for function. That's the typical mode that we would graph something that's in the Cartesian form, with the y on the left side and everything else on the right. The second option, par, is short for parametric. That's what we're going to do right now, is we're going to change that option so that it's in the parametric form. Pol is short for polar. We'll talk about polar coordinate systems a little bit later this chapter. And then SEQ is short for sequential. We're not going to deal with sequential things in this course. Okay. So I've changed my mode to parametric. Now I'm going to press the y equals button. And I have some stuff here that I'm going to clear out. But notice here the slash indicates a single function. So I have a spot for my x coordinate that's written in terms of t, and my y coordinate that's written in terms of t. So in the first row, I'm going to type in t squared plus 1. If you type the variable button, you notice that instead of giving us an x this time, it's automatically giving me a t. The calculator knows that you're in parametric mode, and it's going to give you a t instead of an x automatically. So I'll do t squared plus 1, and then I'll do 2t. Everybody okay there? That's t squared plus 1. It's the same thing that we had written here, James. Okay. Everybody okay so far? All right. Next thing I'm going to do is go to my window now. So the first thing I want to do is change my t-min and my t-max to represent the interval that I'm graphing over. So for this first example, I'm going to graph over the interval from -3 to +1. So I'm going to change the t-min to -3 and the t-max to +1. And as far as the t-step goes, I'm really never going to change that as long as you have something that's reasonably small, like the one that I have here, would be perfectly fine. And notice that my x-min and x-max are all kinds of kooky because I was graphing some things in some other classes. So I'm going to change those back to just be -10 and +10 for the y-min and y-max and x-min and x-max. And then I'm going to go ahead and hit graph. So you should get something that looks like this. What? Okay. Look at this graph for a moment. Do you notice anything about this graph? Looks like half of a parabola, or part of a parabola anyway. Sure. What else? Miguel says it's not a function. Why do you say that? It fails a vertical line test. Now, when we graph things on our calculator in Cartesian form, were we able to graph things like that would fail a vertical line test? Not really, right? We'd take some manipulation to kind of get that to work. In parametric form, piece of cake. We can all graph all those sorts of things. And although when we talk about a Cartesian form, we would not consider this a function, in parametric form we still do. Because our variable is not x or y, our variable is t. So this is still a well-defined function in terms of t, where it wouldn't have been a function in terms of x and y. So if we think about this from a very abstract perspective, in the parametric form, what we have is a function that takes a single variable t and maps it to an ordered pair xy, right? In the Cartesian form, our function took a variable x and mapped it to a variable y, right? So here, in parametric form, even if our x's and y's like fail a vertical line test, this is still a well-defined function because t is only mapping to a single point, right? It's still a function. Whereas if we're talking about in terms of x and y, if x goes to more than one y, that's a problem. But for parametric, our variable is not x and y, our variables are t and then the ordered pair x, y. So it is still a function because of that. Now that's a little bit abstract and maybe not easy to see that subtle difference there, but it's not critically important either. Just that it's okay to fail vertical line tests for parametrics. That's okay. Not the same test.
Is this calculus? Is this pre-calc?
Yeah, this is pre-calc.
Okay.
This is a pre-calc topic for sure.
I sometimes we can't hold the difference whether it's string or whether it's pre-calc.
Yeah, this is a pre-calc topic.
Thank you.
Okay.
I'm serious. It's a serious question.
It's fine. You can ask those kinds of questions. So let's go ahead now and change that parameter interval to -1 and +2. So to do that, I'll go back to my window and change my tmin to -1 and my tmax to +2. And then hit graph again. Notice the difference, right? Do you notice any similarity? Maybe you don't yet. Let's go ahead and graph the third interval. So this time we'll graph it over -2 to +3. Okay. They're all parts of the same sideways facing parabola. Exactly right, Lucas. So each of those three graphs was part of the same sideways facing parabola. If we had graphed t to be -infinity to +infinity, we would have gotten the entire parabola. But it's easy to just take part of it by reducing the interval for the parameter to some specific values. Is everybody okay with that idea? Good. Good. Let's graph another one of these. So let's say that our function is x equals sine t and y equals cosine t. Does it appear that we're short some information? Yes. Yes. So Sam's right. It seems like we're missing that interval for our parameter, right? We don't know what values of t we're graphing over. But reasonably, because of the type of function or type of parametric equations we have here, we should be able to reasonably take a good stab at what our interval for this parameter would be. Well, it's an interval, so it has like a start and an end. So a single number would not be a good one for an interval. So what do we think? What is this interval for t going to be? Think about the parametric equations involved. X equals sine t and y equals cosine t. I think that's a bit of overkill. So think about, what do we know about sine and the graphs of sine and cosine? Okay, they make squiggles. So they repeat themselves over and over again, right? What? So how long on the x-axis does it take for it to repeat? 2 pi. So our interval that we want to choose for t should be 2 pi long. So what's an interval that has length 2 pi? 0 to 2 pi. That would be the obvious choice. So we'll use 0 to 2 pi. So let's go ahead and enter this into our calculator now and see what we get. So sine of t, and then cosine of t, and then 0 to 2 pi. Now, before we hit graph, what do you think this is going to look like? What? It's a circle. In fact, what are we really graphing here? This is going to be the unit circle, right? If you think about what is the unit circle, it is a circle whose x-coordinate is cosine of theta and y-coordinate is sine theta. Same thing that we have going on here, right?
Nothing's showing up.
Why would nothing be showing up? Let's think for a moment. So we're graphing things with sines and cosines. We did this last semester. When you typed in your calculator and you weren't getting a good graph, what was likely the issue?
You were in the wrong mode.
You're in the wrong mode. What mode should we be in to graph this? Radian mode. If you got nothing showing up, you're probably in degree mode. So hit the mode button.
I am in degree mode. Now I have changed my as you can see.
So if you change that to radian mode, you should be okay now. Everybody feel good now?
Good God. Almost got cheese.
All right. Hopefully at this point you feel okay about getting these things into your calculator and getting a graph to come out, right? It's not too much to it. What I want to do now is talk a bit about converting in between these two forms. So we have things, stop talking please. We've written things in Cartesian form. We've done that for like 16 years. We've just talked about parametric form. What I wanted to do now is talk about how we can go back and forth, right? So first things first, let's look at going between parametric and back to Cartesian. So let's say we have this parametric function, and we want to get this into Cartesian form. How many variables do we have in a Cartesian form equation? 2. What are the two variables? X and y, right? Everybody's okay with that? How many do we have in a parametric form? 3. We have x, y, and t. So in order to get this parametric equation into a Cartesian equation, we have to eliminate t. Everybody's good with that plan? So we have 2 equations and 3 variables. We should be able to do that, right? How can we get rid of the t? Great. So Mark says we can use like substitution. We can solve one equation for t and then substitute it into the other, or something like that, right? Everybody's okay with that idea? So which one of these 2 equations would you like to solve for t? The bottom one sounds fine. So when we do that, we get t equals 1 minus y, right? Okay. And then what we'll do is we'll just substitute that in to the other equation. Now, does this look like a Cartesian form equation? Not really, right? What does a Cartesian form equation usually start with? Y equals, right? So let's rearrange this so that it has the y by itself. So we'll distribute that 3 through. And then I'll combine some like terms here. I'll add that 1 over and then divide both sides by 3. And there's my Cartesian form equation. Is everybody okay with that? All right. So what kind of function did this turn out to be? Yeah, linear equation, right? This is just a line. Everybody's okay with that? All right. So what we want to do now is we want to figure out the domain and range for this function using what we know about the parametric form. Because the parametric form may not be like all real numbers, all real numbers. It really depends on that interval of t that we're using. So the way this is going to work is that if I think about x equals 2 minus 3t as an equation where t is the independent variable and x is the dependent variable. Everybody's okay with that idea? We're going to have the domain for the Cartesian form is going to be the range for x equals f of t. So what I need to do is I need to figure out the range for this function. Everybody's okay with that idea? So the domain for this function is just going to be the interval for t. So x equals 2 minus 3t is what kind of an equation? It's a linear equation. Very good. The domain for this linear equation is all real numbers, right? That's just from what the interval of the parameter. So what's the range for that going to be then if the domain is all real numbers? Also all real numbers, right? So I know the domain for this is also going to be all real numbers. Now I'm going to look at the y equation. So again, I'm going to think about this as a linear equation where t is the independent variable and y is the dependent variable. So the range for the Cartesian is going to equal the range for y equals f of t. Okay? So if I look at y equals 1 minus t, what kind of function is that? It is a Cartesian function, but specifically what kind of Cartesian function? 1 minus y equals 1 minus t. That's linear, right? That's just the equation for a line. Everybody can see that? Because it's like a degree 1 polynomial, right? So we know the domain for this function is all real numbers. It's just the interval for the parameter. So if the domain for my line is all real numbers, what's the range? All real numbers. So that's the domain and range for this. Let's do another example that's maybe not quite as trivial as this one is. Okay? It'll be a little bit easier to see what's going on if it's a little bit different here. Okay. All right. So here's my parametric form. Let's get this into Cartesian form. So which of these two equations do you want to solve for t? The first one. Great. So when I do that, I get t is equal to negative x over 4. So when I substitute that in, I get 2 times negative x over 4 squared plus 1. How do I square a fraction? We square the top and we square the bottom. And then how do I multiply 2 fractions together? Multiply the tops together and you multiply the bottoms together. So that gives me 2 over 16, or reduces down to just 1/8. So there's my Cartesian equation. Everybody's okay there? Now we have to do the domain and range. Okay? So which parametric equation am I going to use to figure out the domain? I'm going to use the one with the x. Right? Domain is about x's. Okay. What I want is the range of this function x equals negative 4t. It is not all real numbers. Why not? Because the domain is restricted to negative 2 to positive 4. So what am I going to do? So what is my domain going to be then? It's the interval from negative 16 to positive 4. Remember, the small number always comes first when we write our interval. It is not 8 negative 16. That makes no sense. It has to be small number to big number. Is everybody okay with that idea? Okay. Now let's find the range. Which parametric equation are we going to use to find the range? The one with the y. Okay? What kind of equation is y equals, or what kind of function is y equals 2t squared plus 1? Quadratic. How do we find the range of a quadratic function? You need to find the minimum value, which occurs where? What does the graph of a quadratic look like? A parabola. So where's the minimum value going to be at? At the vertex, right? Furthermore, we know this parabola opens up because the leading coefficient is positive. So we know it has a minimum value at the vertex. How do you find the vertex of a parabola? Very good. So that vertex, the x-coordinate is negative b over 2a. That's the part we care about. So what is that value here? 0 over something, which is just 0. Okay? So we need to check that value. And we also need to check the other 2 endpoints of our interval. Yes. Yes. Oops. It's not.
Something equal 1 when it's 2 to the 0 power?
Yes. Yep. Anything other than 0 to the 0 power is 1. 0 to the 0 is undefined. Undefined.
Oh,
Because it means 0 divided by 0.
oh.
Okay. So, when I do that, what I'm going to do now, I want to go from min to max. Which one is the smallest of these three?
1.
Which is the biggest?
30.
33. So my range is 1 to 33. Is everybody okay there? Does that feel a little bit better after we do something that's a little bit more, I don't know, I want to say complicated, but a little bit more involved than just the all real numbers everywhere, it's all real numbers. Yes? That should feel a little bit better, I hope. Okay. Yes, Abby. Sure. All right, let's do another one. Again, we're trying to get this into Cartesian form. So we have the parametric equation. X is equal to 3 cosine t. Y is equal to 3 sine t. Are we going to be able to eliminate our value, or eliminate the value? Are we going to be able to eliminate t the same way we did before? No, right? Why not? What's going to be the problem? We have these sines and cosines. Sure. Why is that an issue? Well, you can do like the cosine inverse of both sides to get the t by itself, but what's the issue with doing that? Well, the issue, it's a domain and range issue for these two functions. Remember that the domain for sine and cosine is all real numbers. The domain for an inverse is like -1 to +1. So like you're going to get some mismatch stuff going on, and it doesn't really work out. So we're not going to be able to do this the same way we did before. So when in doubt, let's look at the graph of this and try to make try to figure out what's going on. Maybe an idea will present itself. So we have that, 0 to whatever. Okay. So here's my graph. What is the shape of this graph? Circle. Wonderful. Who remembers what the general form equation for a circle is? Well, that would be a unit circle centered at 0, 0 would be x squared plus y squared equals 1. But we're just talking about a general equation for a circle, any circle. So our general equation for a circle, x minus h squared plus y minus k squared is equal to r squared, where hk is the center and r is the radius. So if we look at our graph, what is the center? Center for this circle? 0, 0. What's the radius for this circle? No. Look at the tick marks. One, 2, 3. If you did it on your own calculator, you would have been able to see that. Okay? So if we do that, what are we going to get? We plug these into the equation we have above. We get that, right? X minus 0 squared plus y minus 0 squared equal to 3 squared. That should be our Cartesian form, right? Let's verify this. So if I take x squared plus y squared, what I'm going to do now is I'm going to substitute into this my parametric equations. Everybody's okay there? Right? Because I know x is equal to 3 cosine t, and I know y is equal to 3 sine t. So I'm just verifying to see if the equation that I wrote above is correct. So 3 cosine t squared is 9 cosine squared t, and 3 sine t squared is 9 sine squared t. Everybody agree with that? Do you notice there's a greatest common factor there? That I have a 9 in common to both terms. So I can factor that 9 out. Do you notice anything here? Sine, or cosine squared plus sine squared is indeed 1. So we get 9. What were we expecting to get?
9.
X squared plus y squared is equal to 9. What do we have? X squared plus y squared is equal to 9. We got it. Everybody feel good there? Okay. Next up, we're going to go from Cartesian to parametric. Okay. Do you guys want to do this the hard way or the easy way? Dude, you are such a liar. You definitely want to do it the easy way. Okay? Yes, of course. So we're going to write this as a parametric equation. So the easiest way to do this is we're just going to set x equal to t. We're going to make that our first parametric equation. If x is equal to t, what does y equal? 3t minus 2. Everybody's okay with that? Great. So then what is the interval for our parameter got to be? Okay. So if x and t are the same thing, right, in this situation, if x and t are the same thing, then all the values I can have for x are the same values I should have for t, right? So what's the values I can have for x in y equals 3x minus 2 is just the domain for 3x minus 2, which is all real numbers. So the interval for t should be, negative infinity to infinity. That's the other big advantage, is that the domain for the Cartesian function will just be the same as our interval for the parameter, as long as we just pick x equal to t. So it just makes life very, very easy if we approach it in that fashion. Oops, I should probably say A, because that doesn't have to be specific. Let's say that we want to find the parameterization of a line through the points 3, 9 and -5, 2. When I say find a parameterization, what are we really asking for? I want the parametric equation, yeah. Everybody's okay with that? Okay, so what's one way we could do this? Should be one way that's quite obvious. Exactly right. So we have 2 points. We can write the equation for the line that passes through those 2 points, and then take that equation and turn it into a parametric equation, doing the same thing that we did in the previous example. Perfectly reasonable way to do that. That should be relatively clear now that I've kind of just talked through it. We're just using a bunch of Algebra 1 skills. I'm going to present you with another way of doing this, though, that's a little bit easier, I think. What I'm going to use is my vector equation. Okay. So remember our vector equation for a line was this, right? Everybody kind of remember that? What was R naught? Yeah, what was R sub 0? That was a point vector, so I could use either 3, 9, or I could use 5 or -5, 2. It doesn't really matter, right? What was vector V? That was the slope vector, right? So I can use either AB, or the vector AB, or I could use the vector BA. It doesn't really matter. Let's use the vector, hold on a second, AB. So to do that, I'm just going to do head minus tail, and then head minus tail. Actually, this is BA. Excuse me. Everybody's okay there? Everybody's okay with this? So there's my vector equation for a line. You want to use 3, 9? You could use 3, 9. That's fine. You're good? Okay. So that's everything I need. So that tells me that my x is going to be -5 plus 8t, and my y is going to be 2 plus 7t. Everybody's okay there? And because the line extends in both directions forever, what should be the interval here? Yeah, -infinity to +infinity. So the advantage of doing it this way is when, after we write the equation for the line, there's no rearranging to do, there's no vector. All we have exactly what we need to write our parametric, right? That's the advantage of treating this as a vector problem rather than a Cartesian problem. Huh? And. So here we want the parameterization of the line segment through the points -1, 4 and 6, -3. What's going to be different about this problem than the previous one? It's a segment, so the interval for t is going to be finite long, right? So let's start by getting the parametric equation first, and then we can talk about what we're going to do to figure out what that interval is going to be for this. Sound okay? All right. So let's start here by finding my vector v. So in this case, I'm going to find dc. Everybody good there? So for R0, I'll just use the first point. So there's my vector equation for the line. Everybody's okay there? Okay. So, since our vector line equation is using one of our 2 points, what value of t are we definitely going to need to start or end at? 0, right? If t is equal to 0, I get the point -1, 4. That's either going to be the start or end of this segment. Everybody agree with that? Okay? The other endpoint I should be able to get at either t equals +1 or t equals -1. It's not entirely clear just by looking at this problem which one's going to be. So to check, I'm just going to check. All right, what do we get when t equals 1? I get -1 plus 7, and then 4 plus -7. Is that the point we needed? Yes. So our interval then just is from 0 to 1. If that wasn't the point I needed, I would try -1, and that one should have worked. What do you guys think? Yeah, I think that's probably good for today.